All right. Well, yeah. Sucks for those of you that are not here. I'm sorry. No, but if there's any question of the slides that went, let me know. And if you're listening on Zoom, and I can see you in an office hours, but should be clear. So we're trying to find the inverse kinematic for this robot configuration. We're trying to find theta 1 and theta 2. Use law of cosine twice to come up with theta 1 and theta 2. Now, for any given point, we are able to produce theta 1 and theta 2, right? There is one problem we haven't talked about. So whenever you're using tangent inverse, yes, there are multiple solutions, right? There is, because tangent inverse, tangent of x and y, tangent inverse of x and y is equal to tangent inverse of negative x and negative y. Correct? So you can use a tan 2 x and y in MATLAB to get the two argument solution for this. Now you have to check with your previous solution how theta is changing. If you see a big jump, like pi plus the angle that you got, you know that is not the valuable solution, is not the viable solution, sorry, the other solution is acceptable. So you will add that to your code, yes. Well, I use law of cosine. I don't know if you want to use law of sine. I've never heard, I mean, I never used it. You can, but it should give you the same angles. You're probably using it different instead of looking at the angle in front. You're probably looking at the angle on the side, right? If that's what it is. If you're reading your book, you see law of cosine in your book as well. So I suggest use that. For today's quiz, you have to use law of cosine also. So I suggest just using law of cosine, just to make things simple. What time is it? All right, we have time. So this is kind of, I think the last example, it is the last example of geometrical. Now, do you see that here? We kind of came up with an analytical solution, even though it's geometric, but you found an equation for sine and cosine, right? So this is where analytical and geometrical are kind of mixed up because you found an expression. So this is analytical solution, but I still call it geometrical because you used it by observing and using trigonometry, right? So if you heard an analytical solution, that's basically what you're talking about, finding expression for joint variables, all right? And you are able to use your trigonometry, but you have to think about how many solutions that expression will give you, all right? Now let's look at a bigger example. So when we say here analytical inverse kinematic, it means that you can still use geometrical as part of your solution, but there might be other things because so far we only discussed position, right? We said don't look at the orientation right now, just put it aside. Let's find X, Y, and Z. Now, what if you wanted the orientation as well? So we can solve the position from this analytical part, from the geometrical, and then use other tools to find the orientation. All right. So a good example is a Puma robot, which is 6R robot. So there are 3 joints on the shoulder. Well, shoulder has 2, sorry, and 1 elbow, and there's a wrist that has 3 rotations about X, Y, and Z. All right. So you'll see there are different Puma robot with different numbers, like Puma 560. And like if you look, you'll see different numbers, and the number or the model is the configuration of the robot. But there's always 2 revolute joint on the shoulder. So here is shoulder 1. This is shoulder 2. And this is elbow. And this whole thing is wrist, which has 3 revolute joint. The third one is not shown. The third one is here. You could also see 2 rotation and 1 translation. So in this kind of situation, if you look, you will see that the position of this wrist only depends on the previous three revolutions, right? So if I want to find the position of the end effector, I can disconnect the joint, the wrist joint, right? And only solve for the first three to find the position. And then I can add this back to find the orientation. So that's how we will solve this kind of problem. So for every robot that you will solve the inverse kinematic, there is no straight one answer. You have to look at the robot and see if you can divide that into sub-problems. So sub-problem for position and orientation sub-problem. But this example is also from your book, but I'm only going to show you the sub-problems, how we deal with them. I won't go into detail because it's not going to show up on your exam. And but I want you to go over from your book, and if you have questions, then I will answer. There is a stamp for robot right after, so it will be 2 examples of the same method. All right, but you'll see that for the position, they're using geometrical method that we already discussed a few times with few examples. So these are the specification of this Puma robot. So here, basically says that this is the z-axis, so this is z1. This is your z2. It could be also in this direction. It will depend on which direction your robot is moving. And this is z2, z3. So these two are rotating the same direction. So they have their z-axis are parallel. The z-axis of the shoulder is pointing upwards. So the base is rotating this way, and then the arms, kind of like human body. But instead of 3 joint for your shoulder, you only have 2 and 1 elbow. All right. And then there's a wrist, and there are 3 rotation revolute joint at the wrist. One in the direction of x0, the other one in the direction of y0, and the other in the direction of z0. So you can reach to all through the space with your wrist. So this is going to be 3R, 1 joint in x0 direction. So where is x0? We will define z0, x0, y0 at the base, right? So one's going to be in the x0 direction, 1 joint in y0 direction, and then 1 joint in z0 direction. And the reason we pay attention to this is that it's going to impact the orientation of the end effector, right? So if you didn't have the direction, you have to look at the robot itself and find out which direction, what is the rotation axis for each joint. All right. So once you define that, you'll see that 4, 5, 6 will identify the rotation, and the first 3 are the only that identify the position. Now we're going to deal with the position problem first, because only involves 3 joints, 1, 2, and 3. So your robot will reduce to something like this, right? You'll have a base, well, which is shoulder 1, shoulder 2, and then you have your elbow. Then what do we have to find here? What are our joint variables? Theta 1, theta 2, theta 3, right? So the best is to find theta 1 first, and because we have px and py, we can find theta 1 from that. Once we have done that, then you will find theta 2 and theta 3. They are in the same plane, theta 2 and theta 3. So if we change the plane to the plane of theta 2, theta 3, we can find those 2, right? So the first one is in x0, y0 plane. Then we move the plane to z0 and y0 to find the other 2. Make sense? So that will be your 3 theta. So once we found that, the details are in your book. I would be just showing you the same equation. We wouldn't have time to go through, but make sure to review those. But once you have that, you will go about solving the orientation problem. Now, if we write forward kinematic expression for this, let's say POE, you can also use DH table. It doesn't matter. So you'll see that for kinematic, we have T of theta, or transformation of the end effector, right? Which we have all the information because we know the end effector position and orientation, right, is given. So we have this part. Then theta 1, theta 2, theta 3 already solved. We also know S1, S2, S3, so we can find bracket S1, bracket S2, and bracket S3. How do we know? We have the direction of the rotation axis, right? So we know 1, 2, 3 item here. We also know M position, right? So how do I rearrange this to find theta 4, 5, 6? We can bring all of this to the left side and bring all of the known items to the right. So we know everything on the right. So this is transformation. This is the transformation, right? This is exponential coordinate of the transformation. So we can put all of this together. Is going to give us a 4x4 matrix, right? We know that e to the power of s theta is a rotation matrix, right? So we can call this, we can say this is a rotation matrix. Now we have e to the power of theta 4, like these three expressions equal to a rotation matrix that we know what is. Again, this is 4x4, right? So it has rotation and a position up to that point. So when I call it R, I mean elements of orientation exist in this. So now we already know the axis of rotation of our wrist joints, right? One is in X direction, one is in Y direction, one is in Z direction of our base frame. So let's say omega 4, the fourth joint is in Z0 direction. So we can write omega, correct? So this is Z0 direction, this is Y0 direction, this is X0 direction. So just by looking at our robot, looking at the configuration, we can write the omega, our screw axis. So we can find S1, S2, S3, bracket S1, bracket S2, bracket S3, right? So again, these are also the exponential coordinate. So I can find a rotation matrix correlate to them. Since I already know the axes, I only need to find the angle, right? So do you remember we have a general equation for axis angle? So we already know what axis is. You know the values. We're trying to find theta. So we are missing theta 4, theta 5, theta 6. We already know what this is, 4x4 rotation, position, and orientation. This looks like a ZYX Euler angle. Or I can also call it here. So Euler angle with rho PCR. That's one way of finding, because we have three distinct joints. We need three distinct joint variables, each about one axis. So that only happens from the rho PCR method, right? Or you could also use, if you wanted, the Euler angle to say that, okay, I'm only rotating about two axes, but then you have to make sure you reach to those orientations. The best is to use three distinct values. Then you will have to solve this. The solution now is analytical. In appendix B11, you have the solution. You code that, and then you'll find what the three thetas are. You already found theta 1, theta 2, theta 3 from your geometrical solution, and then you find these three, from here. Again, you end up at an expression, and then you have a pre-solved solution. We'll grab that and code it. So this is only useful if your robot looks like a Puma robot that you can divide it into two sections, right? Position subproblem and orientation subproblem. Now, what if your robot doesn't look like that? Well, you have to see if you can divide it at some point to find position orientation. If it's not, if it's impossible, then you probably have to move to numerical solution instead of using this method. So there are three different methods to solve inverse kinematic. Based on what you've been asked, you see which one is easier, right? So numerical is when you cannot solve from these two ways, easier ways, then you have to use numerical. what does numerical look like? You know the position of the end effector, you start giving like random values, you start from an initial value to each joint, solve, see how far you are from it, you change the value, solve again, until you reach to a threshold that you're happy with, or exact position, okay? The numerical value is also in your book. I'm not gonna bring it in exam or in any of your assignments, so I'm not pushing it. So we won't spend lecture time on it, but if you had questions, you can come to me and we can discuss. Is Newton-Raphson method is very straightforward, basically what we just discussed. All right. Does this make sense? So this is the end of our inverse kinematic. So if you understood geometrical method well, you can always find the solution to position. The orientation is what makes it more complicated. And then you have to think, can I separate them or not? Now, let's take the quiz. So you have seen this question in the quiz before, but I want you to try to solve it. Everybody knows the solution, okay? But I want you to try to solve. You kind of went over it today. The password is fall 2021, yes. So fall 2021, all lowercase, no space between them. You have to submit in 20 minutes, and I think it's more than enough.